This lecture starts off chapter 4 from the book, which deals with the dual of a linear program. Now, the dual is an important concept for linear programming. In this section, we are going to cover what's in the book, plus we're going to cover a little bit more of the theoretical side behind a dual. So, here's the idea of duality. In general, if we have a standard maximum problem, so the classical linear program where you're maximizing something, all of your constraints are greater than or equal to constraints, all of the coefficients on the right hand side of your constraints are positive. This is called a standard maximum program. In addition, all the variables are non-negative. The dual of this will be what's called a standard minimum program, where your objective function is minimizing, all your constraints are greater than or equal to constraints, and all of the variables are non-negative. Now, when I talk about the dual, we're going to see in a minute how to create the dual. But keep in mind that the key thing here is that the dual is going to give us a second linear program related to the first one that is going to have the exact same optimum value. That is the crux of a dual. So here's an example. This is a linear program and it's dual. So if we take the one on the left as the original one, we'll call that the primal linear program. The one on the right is called the dual. Notice that we change maximize to minimize. And what we are going to do is essentially assign a new variable to each row in the column, each constraint in the program. So this is going to be A, this is going to be B, this is going to be C. So those are my new variables. You can see those are the variables that appear in the dual. And now we start constructing it using those variables. So we had a maximize, we change it to a minimize. If we started with a minimize, we would change it to a maximize. We create a new variable for our objective. So we were doing U before, now we call it W. But look at the constraints. The constraints are 12A plus 9B plus 20C. Look at the right-hand side of our constraints. 12A plus 9B plus 20C. So the new coefficients in our objective function, we get them from the constraint values in our primal function. Now what about our constraints? Well, in the classic problem where you have all less than or equal to's, the constraints become greater than or equal to's. There is one constraint per variable. So the first constraint relates to the x variable that we had in the primal. The second constraint is y. Two constraints in the primal, or sorry, two variables in the primal means two constraints in the dual. Where do the numbers come from? Look down your constraints in the primal. What are the coefficients? 1, 3, and 7. 1a plus 3b plus 7c is greater than or equal to 5. Well, that is the value of x in our original objective function. Our second constraint, this is the y constraint. It's greater than or equal to 2. 2 was the value of the coefficient in the primal objective function. What are the coefficients? 3, negative 4, and 8. That's 3, negative 4, and 8. Those are the three coefficients in our primal constraints. So you can see this is how to create the primal, or create the dual from the primal. Another thing to note is that what if you take the dual of the dual? So we've taken the primal, we've taken the dual of it, and created a new linear program. What if we then take that linear program and create another dual? You get right back to the primal. So this is creating a dual is an operation that if you do it again, returns you back to what you started with. Now in the book, they talk about creating a dual from an equation form linear program. This is a little bit more general than what I just showed. What I just showed is kind of how it's normally presented. The book gives you a bit more of a general way of creating a dual. It creates a dual variable for each primal equation, the same way as we saw. Every primal equation, that should be primal constraint equation. There is a new variable created for every one of those. The constants for the coefficients for the dual objective are again created in the same way. So the dual objective, the coefficients of it, are taken from your original constraints in the primal. And then we create a dual constraint with a constraint typeset set by dual problem type. And I'll show you what this means in this example. So here's an example. What they are doing is essentially putting it into slack form. They're making all of the constraints equalities by adding slack or surplus variables where required. Not artificial variables, slack or surplus variables. So in this case, if we have this example as our starting primal, you can see I've created an equal, one that's already equal, one that's a greater than or equal to, one that is a less than or equal to. And we've seen how to add in slack or surplus variables to make things into equalities. So here all I did was I added in a surplus variable and a slack variable so that my constraints are now equal. Now there is a rule when you're creating a dual problem. If the constraint is equal, then your variable is unbounded. So in our case here, we are going to assign a new variable to each constraint. So we assign y1, y2, and y3 to the three constraints in term. The constraint for each of these now is equal. That means our dual variable is unbounded or unrestricted. So we'll keep that in mind. So what do we do now? Well, now we follow the same pattern that we had before. We had maximize u, we change it to minimize w. Our objective function, we use our coefficients, our constants from the constraint equations. So if you look at each of the equations, we have 12y1 plus 9y2 plus 20y3. That becomes our objective function. It's a minimize, so because we're minimizing, everything becomes a plus or a greater than or equal to. If the dual was maximizing, it would be the other way around. But if the dual is a minimize function, then you want your constraints to be greater than or equal to. And then for our new constraints, we create them the same way. That first constraint, we have one constraint for every one of our original variables. And this time, it includes the new ones we stuck in, the x3 and x4. So there's one for x1, one for x2, one for x3, and one for x4. And now we read down in the constraints. So just to try to make this a little bit easier, I'm going to take this equation, the equality equation, and just put the things into a chart. So we have x1, x2, x3, and x4. Our constraints, our new variables are y1, y2, and y3. And our z, or sorry, it's not a Z in this case, it's a U. And across here we have a W. So what do we have? For our Y1 constraint, we have 1, 3, 0, 0. For our Y2, and our number on the right-hand side is 12. For our Y2, we have 3, -4, -1, 0, and 9. For our Y3 equation, we have 7, 8, 0, 1, and 20. Then the U is our objective function, which has a 5, 2, 0, 0, and then don't worry about that. So now, what do we have? We have the rows of this represent our original constraints. If we start reading down the columns, we get what is going into our dual. So our first constraint is 1y1 plus 3y2 plus 7y3 is greater than or equal to 5. So you can just read it off. All the way along, you get 1 for each of your 4 constraints. Now I talked about how if you have equalities to start with, your final variables are unconstrained. So you have y1 is unrestricted. What about y2 and y3? Well, we ended up there. We said that they're unrestricted, but we also had additional constraints that -y2 was greater than or equal to 0, y3 is greater than or equal to 0. That kind of overrides it. So we have that y2 is less than or equal to 0, and y3 is greater than or equal to 0. But y1 is totally unrestricted. It could be any value. That's our dual. And that's how we can create a general dual. Okay, so this was a very quick lesson that talked about just how to create the dual. Next time, we're going to look at the dual a little bit more detail.